Hello class, today we'll be doing chapter 5, number theory in the real number system. We'll be looking at exponents and scientific notation. Our objectives today are to use properties of exponents, convert from scientific notation to decimal notation, convert from decimal notation to scientific notation, perform computations using scientific notation, and solve applied problems using the scientific notation. Now, let's first look at properties of exponents. So our first property is the product rule. B raised to the m times b raised to the n equals b raised to the m plus n. When multiplying exponential expressions with the same base, we're going to add the exponents, but the base does have to be the same. We're going to use this sum as the exponent of that common base. So here, if I had something like 9 to the 6th times 9 to the 12th, that would be the same thing as 9 to the 6th plus 12. 9 being our base, 6 and 12 being our exponents. Because they're multiplied here, we're going to add them. 6 plus 12 is 18. So my common base, 9 raised to the 18th, would be my simplified version. We also have the power rule. B to the m to the n is the same thing as b to the m times n. When an exponential expression is raised to a power, we multiply the exponents. We place the product of the exponents on the base and remove the parentheses. So, in the example I have over here to the right, 3 raised to the 4th to the 5th equals 3 raised to the 4 times 5. 4 times 5 is 20, so we have a base of 3 raised to the 20th power. It gives you a secondary example here. 5 raised to the 3rd raised to the 8th is the same thing as 5 raised to the 3 times 8. 3 times 8 is 24. So I have my base 5 raised to the 24th power. Up next is the quotient rule. We have b to the m over b to the n is b to the m minus n. So if I have my same base here, but I have a division going on, I'm going to subtract my exponents. So it says when dividing exponential expressions with the same base, subtract the exponent in the denominator from the exponent in the numerator. Use this difference as the exponent of the common base. So here if I had 5 to the 12th divided by 5 to the 4th, I would have 5 to the 12 minus 4. 12 minus 4 is 8. So my common base 5 here would be raised to the 8th in the simplest form. Or if I had 9 raised to the 40th power over 9 raised to the 5th power, that would simplify to 9 raised to the 40 minus 5, which is 9 raised to the 35th. The zero exponent rule says if b is any real number other than 0, b raised to the 0 is 1. So any number other than 0 raised to the 0 is 1. So let's use this zero exponent rule to simplify the following. And it is already done for you. 7 raised to the 0 would be 1. Pi raised to the 0 would be 1. Negative 5 raised to the 0 would be 1. Negative 5 raised to the 0 would be negative 1. Now this last one might throw you for a loop here. But what we can see with this last one is that this negative 5 is not included in this exponent. Here it is, and that's indicated by the parentheses in part C. But in part D, only the 5 here is raised to the exponent of 0, not the negative. Therefore, the negative stays out front, and we have a negative 5 raised to the 0 being negative 1. The 5 raised to the 0 is the 1 part, but the negative part is not raised to the 0, so it stays negative. The negative exponent rule is the next rule we will look at here. If b is any real number other than 0 and m is a natural number, b raised to the negative m equals 1 over b to the m. So we basically have gotten rid of the negative in the exponent by dropping it into the denominator. We've essentially taken our base raised to the negative number, dropped it into the denominator, and put 1 on top. So we're going to use the negative exponent rule to simplify the following. It is already done for you, but we'll work through it and talk through it as necessary. Our original problem here for A is 8 raised to the negative 2. To make and get rid of this negative exponent, I drop it to the denominator. So I have 1 over 8 raised to the 2, or 8 squared. 8 squared is 8 times 8, which simply gives me a 64. So 8 to the negative 2 simplifies to 1 over 64. 5 to the negative 3. To get rid of that negative in my exponent, I drop it into the denominator. 5 to the third is 5 times 5 times 5, which is just 125. So I'm really just looking at 5 to the negative third being 1 over 125. If I look at 7 to the negative 1, I'm going to drop it to the denominator to get rid of the negative. And I'm looking at 1 over 7 to the first. 7 to the first is simply just 7. So I'm just looking at 1 over 7. A positive exponent tells us how many zeros follow the 1. For example, 10 to the 9th is a 1 followed by 9 zeros. So if we look at that expression written out, you can see here we have our 9 zeros and then our 1. So 10 to the 9th is 1 followed by 9 zeros. And if we look at this number, this is our thousandths, this is our 10,000ths, 100,000ths, millionths, 10 millionths, 100 millionths, billions. So if we're looking at 10 to the 9th, that is literally 1 billion. A negative exponent tells us how many places there are to the right of the decimal point. For example, 10 to the negative 9 has 9 places to the right of the decimal point. So if we look at this here, we're going to make sure that when we go right of this decimal point here, that we have 9 zeros here. We're not counting the 0 in front of the decimal point. We're only counting the zeros behind the decimal point. 1, 2, 3, 4, 5, 6, 7, 8. And then the 1 would be in the 9th decimal place. The 9th decimal place. Okay? So, each one of these zeros here, 1, 2, 3, 4, 5, 6, 7, 8, and your 1 goes in the 9th decimal place from the decimal. So, the reason we review this is essentially how scientific notation is built. Scientific notation. A positive number is written in scientific notation when it is expressed in the form a times 10 raised to the n, where a is a number greater than or equal to 1 and less than 10. So a has to be between 1 and 10. A can be 1, but it cannot be 10. It has to be strictly less than 10. And n is an integer. If n is positive, we're going to move the decimal point in a to the right n places. And if n is negative, we're going to move the decimal point in a to the left the absolute value of n places. So write each number in decimal notation. Okay, in our first example here with a, we have 1.375 times 10 to the 10th. Because we have a positive exponent here on our 10, we're going to move our decimal 10 places to the right. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Each place that's not already filled here. Oops. Let me try this again. My pen jumped on me. So let's try this again, just to make it clear. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Technically, every place that doesn't already include a number would be an additional 0. Sometimes it helps to rewrite it and then move it if you've got some space issues like what I had. So we would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. and we would put zeros in for each of these empty holes. So the number we would be looking at is 1375, and then 1, 2, 3, 4, 5, 6, 7 zeros. We can throw some commas in here to try to help us figure out what this number is. So we're looking at thousands, millions. Looks like we're looking at 13,750,000,000 would be our number written out in our standard form versus our scientific notation form. Now in part B, we have a negative in our exponent, which means that we're going to move our decimal that many units to the left. Okay, so here we're going to move our decimal 4 units to the left. So we're going to go 1, 2, 3, 4. And we're going to fill the circles the same way. So we should wind up, and I'll rewrite it just so you might can see it a little clearer. I'm going to move that decimal 1, 2, 3, 4 places to the left. Fill these empty holes with zeros. I'm looking at decimal 0, 0, 0, 1, 1 as my solution in standard form for part B. Now in each case we use the exponent on the 10 to move the decimal point. In part A the exponent is positive, we move the decimal point to the right. In part B the exponent is negative, so we move the decimal point to the left. As we could tell, that's exactly what we did to get our answers. We got the exact same answer for A by moving our decimal 10 places to the right. And we got the exact same answer for B by moving our decimal 4 places to the left. To write a number in the form A times 10 raised to the n, or to write it in scientific notation, we first need to determine A, the numerical factor. We need to move the decimal point in the given number to obtain a number greater than or equal to 1 and less than 10. Then we need to determine n, the exponent on 10 to the n. The absolute value of n is the number of places the decimal was moved. The exponent n is positive if the given number is greater than or equal to 10, and negative if the given number is between 0 and 1. Let's look at an example. So, in this first example, we want to write this in scientific notation. In order to do this, we have to look at our overall number and figure out where we would need to put the decimal to make this number somewhere between a 1 and a 10. We wouldn't want to put it behind the 6 here because 46 is bigger than 10 and I need the number itself to be between 1 and 10. The decimal in this case would need to go between the 4 and the 6. So it would need to look like 4.6. Now the problem is we're looking at 4,600,000 here. We're not looking at 4.6. But when we put it in that scientific notation and multiply it by 10 raised to the n, it will be in scientific notation. We're going from a very large number to a very small number. So our exponent on this 10 is going to be positive. How many places did I have to move the initial decimal, which is technically here, to get it to be between the 4 and the 6? I had to move it 1, 2, 3, 4, 5, 6 places. So I should have it in scientific notation looking like 4.6 times 10 raised to the 6th. Now in B it's a little different because B is a really small number that's between 0 and 1. That tells us that our exponent on our 10 is going to be negative. But I still need my overall number to be between 0 and 1. Now if I move my decimal before the 2, that number is going to be too small because we want our number here to be between 1 and 10. And 0.23 is not between 1 and 10. If I put it behind the 3, that's also not going to work for scientific notation because our base number out front needs to be a number between 1 and 10. 23 is greater than 10. That doesn't work. So the only place I can put this and get a number between 1 and 10 is if I put my decimal, oops, what is up with my pen? Why did it stop working? Is to put my decimal between the 2 and the 3. Right there. So I need to have a 2.3 times 10, but it has to be raised to an exponent so I can get back to my original number. Now, like I said, this is a really small number between 0 and 1, so I know my exponent is going to be negative. For larger numbers greater than 1, my exponent is positive. But for numbers between 0 and 1, my exponent is negative. Now, I'm going to move this decimal 1, 2, 3, 4, 5 places to get to that 2.3. So I'm looking at 10 to the negative 5. If we look at our solution here, we see it breaks it down pretty much the same way. 4,600,000. The number is greater than 10, so n is positive, and a times 10 to the n. So we want to move the decimal point in 4,600,000 to get 1 less than or equal to a less than 10. The decimal point moved 6 places from the 4,600,000 to the 4.6, which is how we got the 10 to the 6. In B, the number is less than 1, so n is negative, in the a times 10 to the n. We want to move that decimal point in 0.000023 to get a 1 less than or equal to a less than 10. The decimal point moved 5 places from 0.000023 to make it the 2.3. That is why we represent the 10 to the negative 5 there. Computations with scientific notation. We use the product rule for exponents to multiply numbers in scientific notation. So if I'm looking at a times 10 to the n plus b times 10 to the m, I'm really looking at a times b times 10 to the n plus m. I add the exponents on the 10 and multiply the other parts of the number separately. So let's look at this example here. I have multiply 3.4 times 10 to the 9th times 2 times 10 to the negative 5 and write the product in decimal notation. Okay. My solution here. I take my initial problem, the 3.4 times 10 to the 9th times 2 times 10 to the negative 5, which is 3.4 times 2, and 10 to the 9th times 10 to the negative 5. I'm essentially taking my base terms and multiplying them, and because the 10s are a common base, I'm multiplying them. What that's going to allow me to do is use my properties of my exponents. I'm going to be able to take my exponent here, 9, and add it to the negative 5 on my 10 for my simplification. Now 3.4 times 2 is simply 6.8. That's where that comes from. I reduced this 10 to the 9th times 10 to the negative 5 down to the 10 to the 9 plus negative 5. And we know that 9 minus 5 is 4. So this number simply reduces to 6.8 times 10 to the 4th. Now this is the scientific notation of those two numbers multiplied, or two sets of numbers multiplied. But if I wanted to write it in a standard form, I would simply write 68,000. And all I did to get there was take the 6.8 raised to the 4th, raised 10 to the 4th, and I moved that decimal those 4 times and replaced those empty spots with zeros, and that's how I got 68,000. Alright, so we use the quotient rule for exponents to divide numbers in scientific notation. A times 10 to the n over b times 10 to the m. So we get a over b times 10 to the n minus m. We will subtract the exponents on 10 and divide the other parts of the number separately. So, essentially what you're doing is you got a times 10 to the n over b times 10 to the m. You're keeping the numbers out front and dividing those, and you're subtracting the exponents there on your 10. So, our question says to divide 8.4 times 10 to the negative 7 divided by 4 times 10 to the negative 4. Write the quotient in decimal notation. Our solution here. Now, we're simply going to keep the numbers out front together. That's what it does in the first step, right here. It keeps the 8.4 divided by 4 by itself, and it puts the 10 to the negative 7 over 10 to the 4th by itself. It essentially just regroups those factors. 8.4 divided by 4 is simply 2.1. Now, if I rewrite this and I bring this negative 4 up, I'm essentially subtracting a negative 4 when I bring it up to do this. So what I get is 10 to the negative 7 minus negative 4. Keeping in mind that this technically changes to a plus, minus a negative. So I get negative 7 plus 4. That's where the negative 3 comes from. So I get 2.1 times 10 to the negative 3. That's still scientific notation. We want it in this decimal notation. In order to get it in the decimal notation, I need to move this decimal 3 places to the left. 1, 2, 3. And put it right there. Add my zeros in, and this is why I get 0.0021. That is the quotient in the decimal notation. Let's try to use this in terms of an actual problem. As of April 2021, the national debt was 28.1 trillion, or 28.1 times 10 to the 12th dollars. At that time, the U.S. population was approximately 331 million, or 3.31 times 10 to the 8th. If national debt was evenly divided among every individual in the United States, how much would each citizen have to pay? Solution: the amount each citizen would have to pay is the total debt. 28.1 times 10 raised to the 12th divided among the number of citizens, 3.31 times 10 to the 8th. Let's do this. Let's do the math. Figure out how much each of us Americans owe in this national debt. Alright, so doing the math here, we put the 28.1 times 10 to the 12th on top, the 3.31 times 10 to the 8th on the bottom. Now we are going to pair the 28.1 and the 3.31 together, and then we're going to pair the 10 to the 12th and the 10 to the 8th together. What we see is 28.1 divided by 3.31 is approximately 8.49 if we keep it to 2 decimal places. Okay? So if we keep it to 2 decimal places, it's approximately 8.49. We multiply that times 10 to the 12th minus 8. So 10 to the 12 minus 8 here, because we're subtracting this bottom number to bring it up to the top. We subtract it. 12 minus 8 is 4. So we're looking at each of us owing 8.49 times 10 to the 4th power. Now, we do want that in actual number value here. So 8.49, if we move it 10 to the 4th, 1, 2, 3, 4, I'm looking at $84,900 that each of us owe with the national debt if we broke it up and everybody had to pay the same amount. Better get your checkbook out and start paying up, I guess. Every citizen would have to pay approximately $84,900 to the federal government to pay off the national debt. That's a lot of money, and that was back quite a while ago. That was, the problem said it back in 2021. And since then, the national debt has gone up tremendously. We each owe a lot, but they keep raising the debt ceiling. Modern problems. Anyways, I hope you've enjoyed this lecture and gotten a grasp on this scientific notation. If you have any questions, feel free to reach out to me by email, and I will answer as quickly as possible. Please go on and attempt the homework for this section. If you have any questions, once again, reach out. Please reach out. I would much rather you reach out so I could help you than I never hear from you, because I'm here to help. I hope y'all have a good rest of your day, and I will see you next lecture.